There is a place on Earth where life survives in conditions that should, by every reasonable measure, be completely impossible. No sunlight, no oxygen, crushing pressure, boiling acid. And yet, something is living there. And what that something tells us about the universe might be the most important clue we have in the search for alien life. Today, we're going to explore that clue, and by the end of this episode, your definition of habitable will never be the same. When most people think about life, they picture something comfortable. Warm temperatures, clean air, plenty of water and sunlight. The kind of conditions you'd find in a garden or a forest or a coral reef. And for a long time, scientists assumed that life required those comfortable conditions, that biology was fragile, delicate, easily disrupted by extremes of temperature or pressure or chemistry. Life, in this view, was a thin, vulnerable film on the surface of a lucky planet, dependent on a very narrow set of conditions to survive. That assumption turned out to be spectacularly wrong. And the discovery of just how wrong it was has been one of the most exciting developments in the history of biology. Over the last few decades, biologists have discovered life in places that would have seemed like science fiction just a generation ago. Life in the boiling water of volcanic hot springs, where temperatures exceed 120 degrees Celsius, hot enough to cook an egg in seconds. Life in the frozen deserts of Antarctica, locked inside rocks, surviving on almost no energy at all. Life in the crushing darkness of the deep ocean, miles below the surface, where the pressure would collapse your lungs like a paper bag. Life in lakes so acidic they would dissolve your skin. Life in environments saturated with radiation that would kill a human being in minutes. Life in the hypersaline waters of the Dead Sea, where salt concentrations are so high that most organisms would immediately dehydrate and die. These organisms are called extremophiles, lovers of the extreme, and they have completely rewritten our understanding of what life can tolerate. More than that, they have rewritten our understanding of where in the universe life might exist. Every new extreme environment where we find life expands the map of possible habitats, not just on Earth, but across the solar system and beyond. Let's start with the hydrothermal vents, because they are perhaps the most dramatic example. In the 1977, scientists exploring the deep ocean floor made a discovery that shocked the scientific world. At cracks in the Earth's crust, superheated water was gushing up from below, rich in minerals and chemicals. And around these vents, in total darkness, miles below the surface, was a thriving ecosystem. Tube worms 6 feet long, ghostly white crabs, shrimp with no eyes, bacteria forming thick mats on the rocks. All of it powered not by sunlight, but by the chemical energy of the vent itself, a process called chemosynthesis, where organisms use chemical reactions rather than light to produce energy. This was a revelation. It meant that life did not need the sun. It meant that the energy source for an entire ecosystem could come from the planet itself, from the heat and chemistry of geological processes. And that opened up an entirely new category of places in the universe where life might exist. Places far from any star, where sunlight never reaches, but where geological activity provides the energy that life needs. The implications for the search for extraterrestrial life were immediate and profound. Think about what that means for the moons of the outer solar system. Jupiter's moon Europa, Saturn's moon Enceladus. These are worlds covered in thick shells of ice, far from the warmth of the sun. For a long time, they were dismissed as frozen, lifeless wastelands. But we now know that beneath those icy shells, there are vast liquid water oceans, kept liquid not by sunlight, but by the gravitational pull of their host planets, which flexes and heats the moon's interior. And where there is liquid water and geological heat, there may be hydrothermal vents, And where there are hydrothermal vents, well, we know what can live there. Now let's talk about another category of extremophile that has profound implications for the search for life: the tardigrade. You may have heard of these remarkable creatures, microscopic animals less than a millimeter long that look vaguely like eight-legged bears under a microscope. Tardigrades are arguably the toughest animals on Earth. They can survive temperatures from near absolute zero to well above boiling. They can withstand radiation doses hundreds of times higher than would kill a human. They can survive in the vacuum of space. This was actually tested, and they survived. They can go without water for decades, entering a state of suspended animation called cryptobiosis, and then revive when conditions improve. They have survived all 5 of Earth's mass extinction events. Tardigrades are not extremophiles in the traditional sense. They don't thrive in extreme conditions, they survive them. But their existence tells us something important. Life, once it gets started, can develop extraordinary resilience. It can evolve mechanisms to endure conditions that seem incompatible with biology. And if life on another world has had billions of years to evolve such mechanisms, who knows what it might be capable of surviving? There are bacteria that live in the cores of nuclear reactors, feeding on radiation. There are microbes that survive in the stratosphere, carried up by winds, living in the thin, cold, UV-blasted air at the edge of space. There are organisms that thrive in the hypersaline waters of the Dead Sea. There are bacteria found in the Atacama Desert, the driest place on Earth, that survive for years without any detectable water, waiting for the rare moments when fog rolls in from the coast. Every time we look in a new extreme environment, we find life. Every single time, without exception. This pattern has a name in astrobiology, the principle of life's tenacity, and it is one of the most encouraging findings in the entire field, because it suggests that life, once it gets a foothold, is extraordinarily hard to extinguish. It adapts, it persists, it finds a way. The history of life on Earth is not a story of fragility. It is a story of relentless, creative, almost stubborn persistence in the face of every challenge the planet has thrown at it. If you're enjoying this series and want to keep exploring these ideas, hit that subscribe button. There's so much more to come, and each episode builds on the last. Now, the implications of extremophile research extend beyond just identifying new habitats for life. They also challenge our assumptions about what life might look like on other worlds. If life on Earth can be so diverse, from the familiar to the utterly alien, then life elsewhere might be even more different from what we expect. It might use different chemistry, different energy sources, different solvents. It might exist in forms we wouldn't even recognize as life if we encountered them. The extremophiles of Earth are a reminder that our intuitions about what life looks like are shaped entirely by the narrow sample we have, and that sample may be deeply unrepresentative of life in the universe as a whole. That is both exciting and humbling. It means the universe of possible life is far larger than we imagined, and it means that in our search for life beyond Earth, we need to keep our minds open, very open, to the possibility that what we find might not look anything like what we're used to. In the next episode, we're going to leave Earth entirely and travel to the most promising address in our solar system for finding life right now, a small, cold, rust-colored world that has been tantalizing scientists for decades. The next episode is already there for you, and we're heading to Mars. What scientists have found there recently is something you need to hear. Subscribe and stay in the playlist. This journey is just getting going.